Welcome to AP Chemistry Molecular Geometry, Hybrid Orbitals. Specifically today we're going to be looking at the valence bond theory, understanding hybrid orbitals, sp hybrid orbitals, sp2 hybrid orbitals, and sp3 hybrid orbitals, along with a lot of worked examples along the way. Let's start out by talking about valence bond theory. This explains why bonds exist between atoms. Uses the idea that valence atomic orbitals share a region of space or overlap to allow two electrons of opposite spin to share the common space between the nuclei and form a covalent bond. Let's consider diatomic hydrogen. We know that the electron configuration for hydrogen is 1s1. And in the s orbital, it's going to be a sphere. So here is one of my hydrogens, and here is another one of my hydrogens. Pretty sad looking circles there. So for one hydrogen, that represents 1s1, and for my other hydrogen, that also represents 1s1. And as they come together, they get those two valence electrons they need to form that covalent bond that holds them together. Let's consider hydrogen chloride. Hydrogen has an electron configuration, as we see above, of 1s1. Chlorine has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. If we were to draw a model of hydrogen chloride, we'd say, okay, well, hydrogen is 1s1. And the S represents a sphere. So there is my sphere representing hydrogen in 1s1. The valence electrons in the chlorine are going to be in the p sublevel. And we know that p is represented as a dumbbell. So very carefully, I'm going to draw the p dumbbell here. Not so shabby. That represents chlorine and the 3p sublevel. This overlap right here represents that covalent bond because hydrogen is 1s1, chlorine is 3p5. So if they share electrons, the hydrogen becomes 1s2 and the chlorine fills its octet and becomes 3p6. Finally, we have chlorine gas. And really with chlorine gas, we know that that is diatomic chlorine. So the way that we're going to visualize this is a dumbbell representing one chlorine, so Cl and the 3p sublevel, and another dumbbell representing the other chlorine, as we could see right here. So that's another Cl with its 3p sublevel. And again, we have these shared electrons in between. And those shared electrons will help each of the chlorines fill their octet and form that covalent bond. The interesting thing here is that with the valence bond theory, we don't need to change anything. As these atoms overlap, they share electrons that they need, they fill their octet, and they form the covalent bonds. Now let's talk about hybrid orbitals. When the atomic orbitals in an atom mix to form new orbitals, the shape of the hybrid orbital is different than that of an original orbital shape. So, just so we all remember, an s orbital is represented as a sphere, which we can see right here. A p orbital is going to be represented as a dumbbell, and remember we can have these dumbbells on the x, y, and z axis. And the d orbital is represented as a cloverleaf and other interesting models. Hybridization, the process of mixing atomic orbitals as atoms approach each other to form bonds. The first type of hybridization that we're going to talk about is sp hybrid orbitals. It is possible to create the substance beryllium fluoride, BeF2, due to differences in electronegativity via covalent bonds. First, what is the electron configuration for fluorine? Fluorine is 1s2, 2s2, 2p5. We can represent this as an orbital diagram for ground state fluorine. So 1s2, 2s2, and then we fill in the 2p sublevel with the 5 electrons. And that represents the orbital diagram for ground state fluorine. Now let's look at the electron configuration for beryllium. Beryllium is 1s2, 2s2. The orbital diagram for beryllium would be filled as follows: 1s2, 2s2. In the ground state, there is no unpaired electrons available to bond with fluorine. In order for bonding to take place, one electron from the 2s orbital is excited and promoted to the p orbital. So now when we fill our orbital diagram, it's going to look like this: 1s2, 2s, 2p, because we have an excited electron that's moved up to the 2p sublevel. There is still a problem though. The single electron in the s orbital has a different shape than the single excited electron in the p orbital, with s being a sphere and p being a dumbbell. So we need to mix these two orbitals and create a hybrid of the two. This is known as a hybrid orbital, or a mix of the two. So our orbital diagram would look like this: 1s2, and then s and p. So we are basically mixing these two together. This one electron represents this s orbital. This one electron represents this p orbital. And as we mix them together, we form these hybridized orbitals. So one there and one there. So two sp hybrid orbitals. Ultimately, they're going to overlap and represent sp. The two new orbitals are identical in shape, but the larger lobed end points in the opposite direction of the other. According to the valence bond model, a linear arrangement of electron domains implies sp hybridization. The electrons in the sp hybrid orbitals can form two electron bonds with the two fluorine atoms. So a bond can be formed here and a bond can be formed here, which will result in BeF2. sp2 and sp3 hybrid orbitals. Other combinations of atomic orbitals can be hybridized to obtain different geometries. Consider BF3. What is the electron configuration for fluorine? And we've done this one already, so we know that it is 1s2, 2s2, 2p5. So the orbital diagram for fluorine would look like this: 1s2, 2s2, and the last remaining 5 would fill in as so. What is the electron configuration for boron? Boron's electron configuration will be 1s2, 2s2, 2p1. The orbital diagram for ground state boron would be as follows: 1s2, 2s2, 2p1. In the ground state, there is only one unpaired electron available to bond with fluorine. In order for bonding to take place with all three fluorine atoms, one electron from the 2s orbital is excited and promoted to the p orbital. So our orbital diagram would look like this: 1s2, 2s1, 2p1, 2p2, where we had an electron from 2s get excited and move up to 2p. Again, there is a problem. The single electron in the s orbital has a different shape than the two electrons in the p orbital. So again, it is necessary to mix these three orbitals together and create a hybrid of the three so boron can bond with all three fluorine atoms. This is known as a sp2 hybrid orbital. So our orbital diagram would look like this: 1s2, and then the sp2 would look like that. As a result, 3 equivalent sp2 bonds are made. Now boron has the ability to form 3 bonds as assumed from its 3 valence electrons. Let's see what this looks like. So the orbital diagram for ground state boron begins like this: 1s2, 2s2, 2p1. We excite an electron from the 2s sublevel and bring it up to the p sublevel. So now we have 1s2, 2s1, 2p1, 2p2. These 3 come together to form a hybrid orbital, which is represented as these electrons right here. So the sp2 hybrid orbitals can be seen here, here, and here, and they are a combination of the S and the two P's coming together. According to the valence bond model, a trigonal planar arrangement of the electron domains implies sp2 hybridization. Now consider methane. This is a situation where an s orbital mixes with all three p orbitals in the same shell to give carbon the ability to bond with four other atoms. What is the electron configuration for hydrogen? And we know that hydrogen is 1s1. The orbital diagram for hydrogen would be 1s1, right there. What is the electron configuration for carbon? We know that the electron configuration for carbon is 1s2, 2s2, 2p2. The orbital diagram for ground state carbon would be 1s2, 2s2, 2p1, and 2p2. In the ground state, there is only 2 unpaired electrons available to bond with the 4 hydrogen atoms. In order for bonding to take place with all 4 hydrogen atoms, 1 electron from the 2s orbital is excited and promoted to the p orbital. So now our orbital diagram would look like the following: 1s2, 2s1, 2p1, 2p2, 2p3. And as we could see, we now have the potential for 4 different bonding sites. As before, there is a problem. The single electron in the s orbital has a different shape than the 3 electrons in the p orbital. So again, it is necessary to mix these 4 orbitals together and create a hybrid of the 4 so carbon can bond with all 4 hydrogen atoms. This is known as sp3 hybrid orbital. Our orbital diagram would look like the following: 1s2 and the 4 remaining electrons would make up the sp3 hybrid. So in this case, 4 equivalent sp3 hybrid orbitals are formed. Each sp3 hybrid orbital has a large lobe that points towards the vertex of a tetrahedron. According to the valence bond model, a tetrahedral arrangement of electron domains implies sp3 hybridization. So again, we can see the s and the 3p electrons merging together to make that sp3 hybridization as we see in the model here. So what did you learn? We talked about the valence bond theory. We introduced the concept of hybrid orbitals. We talked about sp hybrid orbitals, sp2 hybrid orbitals, sp3 hybrid orbitals, and did a lot of worked examples along the way. Need more help? Feel free to contact me. Have a great day.